Alright, last day we looked at time order data, and here I want to look at time series like we had last time, where we looked at sunspot data and looking at the monthly sunspots over a couple of centuries of data. One of the things that we notice after different kinds of analyses that there appears to be an 11-year cycle, and that's a principal feature of this data set, is that there's this cyclical pattern over the centuries here, and roughly it corresponds to about 11 years between each of these peaks. We saw that in a variety of ways, just marking it here by colors so that we see that each cycle, with the exception of these misalignments at the beginning, look like they're capturing that V. And we saw those misalignments again when we overlaid the cycles on top of each other. There's sure a general cyclical pattern here, but there are a few aberrant patterns that suggest that we haven't quite got the alignment right. But the principal feature of that time series was its seasonality, this 11-year cycle. We call that a seasonality, even though it doesn't correspond to any Earth season. It comes from the natural change of the seasons on Earth. We talk about the seasonality, but this is an 11-year cycle. Let's look at an earthbound series. And the earthbound series here is carbon dioxide over Hawaii, and this is measured for some time. We have a few decades of data here. This continues to be measured. There's the amount of carbon dioxide measured in the atmosphere in parts per million over various years and at different times during the year. So we have, for every month, we have a measurement going back to March 1958. What we'd like to do is investigate that time series, and you see that there's certainly a seasonality component here, but there's also some sort of growing of the size of the time series, and that it's getting larger and larger over time. The values are getting higher and higher. And we could play in Loon, as we did before, with looking at changing aspect ratios, etc. in Loon, and we're going to look at a plot and layer the time series on top of it, connecting the dots of the plot. I'll just show you some of the features of Loom when we do this. In principle, I'm going to show you things like this, so we can see some labels, which means I had to have this function that will get me some interesting dates for the labels. So let's do that. Let's go to Loon. So here's the code, and we'll just execute that in Loon and find our plot here appearing, and the inspector. I'll just move the RStudio framework out of the way. We know, just as we did with the sunspot data, that changing this aspect ratio allows us to focus on different features. Certainly this aspect ratio that you see here, it's definitely what we see as a trend. The trend's moving up from left to right. That may be more apparent if I were to go to the layers and turn off the dots, turn off the scatter plot. So there's our time series going from left to right. We could change that by changing the shape of the window here, and see there's our trend. So over those couple of centuries, there's definitely an increasing trend in this time series. You'd like to be able to capture that. Now if I were to take that out and just zoom in on, with the control scrolling here, zoom in on these pieces, we can see there's also a cyclical pattern here. These cycles that are going up and down, and when I get close to the 45 degree here, it was showing you the size. You see that it grows more slowly and drops quickly, slowly, drop quickly. More of a sawtooth than a sinusoidal pattern. And if you see over here in the inspector, I can move this window along, these different windows in the time series, and that seasonal pattern, that cyclic pattern, is certainly appearing throughout the time series. And it's roughly the same throughout. Okay, so let's bring the scatterplot points back in, and now let me just zoom in a bit. Here we can see that how big is this cycle. So let me just zoom a bit more. So I've got one of these cycles from trough to trough, and because I've got the item labels here showing on the inspector, you can see when I hold over this, I'll get a hover. So that's from 1987 September to 1988 September. So that is an annual cycle. It's one reason we call it seasonality of these cycles, because it corresponds to the seasons of the year. So what we'd like to do is capture that. So just put this back onto the scale, and we'd like to capture those two pieces, the trend and that cyclical behavior that we have, into two pieces in our analysis. So back to the slides. So that kind of interactive analysis shows you there are a couple of interesting interpretable features of the data set itself, and we might want to say, can we capture those just programmatically? Can we just get some functions that will essentially try to capture that trend and that seasonality that we've observed over time? So here's a very naive way to do this, and what I'm going to do is I'm going to take the data for every year and replace it by the average over all of the values, all of the measurements in that year, and do that for every one of the years from, was it 1959, sorry, I was thinking with sunspots, 1959 up to 97. So I can get an average for each one. And that should give me some sense of the trend. In the same way, I could think about, well, why don't I take every month, take every January, and average the measurements over all years, right? So I take January and I take the Januaries for every year and average those, much like we did before. We can do it now, except we're doing it over months, over years for each month rather than for each year over all months. So to get at that programmatically, I'm going to be able to get some years out of this data and also get the months. And the month numbers will be 1 to 12. Month numbers are very easy. It's going to be just 1 to the frequency of the time series. And the year is a little more of a nuisance, but that's because the time and the time series in R is recorded as the year and then a fractional part of that year for each month. So all I have to do is get the floor of that time series and get the unique elements, and I'll get all of the years. So we need a function that will calculate our averages. So this function, getAvs, is going to take the time series and decision which average are we interested in. Are you interested in the average over all of the months for each year, or are you interested in over all of the years for each month? So get the years, get the months, get the number of years, number of months, and then we decide which average do we calculate depending on if it's over months or not. So if it's over months, that means in every year we want to calculate the average over all of those months. This illustrates a number of functions here. So I'm going to take the supply over this 1 to the number of years that I've got and apply that function to each year. Here will be I, and I'm just going to get the average or the mean of some data. And oops, I'm not going to be able to capture that very well. Okay, mean of some data. And what data is that? Well, it's a window in the time series, a window that starts in the first month of the year I'm interested in and ends in the last month of the same year. Okay, so that's going to average the values over all months in that year, and it'll do that for every year as we go over this list of 1 to n years. If I'm interested in averaging over the years, that is not over the months, then I'm going to have the average is going to be over for each month. I want to average over all of the years, which means I'm going to start with year 1 and the month that I'm interested in, and end with the last year, right, and the month I'm interested in, and I'm going to step over that whole thing. This window is going to be jumping over the full frequency each time, which is going to go every 12 months. So that's going to calculate the other set of averages, the averages for each month. So hopefully this one is going to capture something about the trend. This is going to capture something about the seasonality. So if I do that, here's what the results look like. So averaging over the months, there's my trend from 315, 316. You see it's an increasing set of numbers all the way up to 363. So that's my trend component. Similarly, if I'm looking at averaging over all the years with January to December, I'm starting at 336 here, and ending roughly at 336, and going up 337, 338, up to a high, it looks like, of around here, 339.8, and then decreasing again down to a low here before we start going up again. And you'll notice the unfortunate bit about this one, this average is a little bit higher than that one, so to be smooth, it would have been nicer if that was a little lower. It didn't turn out to be the case. So suppose we plot those. So if I plot over the months, I'm going to plot for each year to see what the trend looks like, and then I'll plot it for the average over all the years to see what it looks like for an average year. So over all of the average for over all months in each year, that is, I can see this trend as year changes, it's increasing, and that's kind of capturing a major feature of the CO2 data, is that it's an increasing trend that's showing no sign of declining in all this set of measurements that we have in the past several decades. But what we've done is, and the way to think about this, I've taken that original series and I've smoothed it out. I've gotten rid of all those little bumps, all those things that are going up and down the sawtooth. And this is a smooth summary of the major feature of this time series. For each month, then, averaging over all years, you can see this cyclical behavior, and it's, again, this is a little higher than that, so that's not so good. But those are the averages over all of the years, and describing what seems to be happening is that the concentration is at its highest in the early spring, late spring, early summer, maybe of the year, and is lowest in its early fall. In the fall, highest in the spring, lowest in the fall, and that's very much a seasonal effect. So to get some sense of what's happening, and then we've effectively decomposed this series into two pieces. Sort of the overall trend, which is describing the major feature of the data, and then this within year pattern, this seasonal effect. We could plot these together simply by just plotting first the data, then the trend, and then the seasonal part. We'll put them all in the same picture. So we have it here. The data itself looks like this, which on this aspect ratio you can see the trend going up in the cyclical behavior, and there's the trend itself, and there's the seasonality with that little blip at each endpoint. So things to note is, because this is a very naive way to approach this, I'll just take an average, which means all of these measurements are on the same scale. So I've averaged things out over different ways, but I've still got, in the 300s on the parts per million, whether I'm looking at the seasonality, which is a bit unfair. That's not really describing the seasonality, because that's describing changes over this whole range. So that's not quite good enough, but it does give you some sense of changing over time. What I really want is this little piece in here and this separated out. So while this kind of captures what's happening, it's clearly not doing the analysis justice. So a slightly more sophisticated approach is that given by decompose. And decompose will decompose, in this case, the time series into additive components that sum, and it can have some structure which you can look at. It'll have a trend and seasonal components and residuals, but it looks like this. And what has this done? So we have the original data here, we have the trend, which is on the same scale as the original data, because that's actually capturing the major feature in this data set. And then we have this nicely seasonal effect here, the cyclic effect that's the same for every year as we go left to right across here, and it's on the order of -3 to +3. And that's kind of the size of this thing, the magnitude of these little guys. So that's the right scale that we've got there. And then this is all kind of noisy stuff. hopefully fairly patternless, no obvious pattern at least, in what this piece is on a much smaller scale, again from minus 0.5 to 0.5. The reason being is that the data is actually equal to this trend plus the seasonality plus these are the minor departures inside here, local departures from the sum of these two. Another way to think about it is we take the data, we remove this trend, subtract off this trend, and then we figure out what the seasonality is, and then we subtract this out, and so this remainder part is entirely the original data less the trend less the seasonality, gives us this leftover or residual piece. So these are our residuals. So how might this do it? So what is actually done for decompose, instead of replacing each little seasonal part here from trough to trough by the average of all the pieces there, what it does is it replaces every point in this whole series by an average. So this point will be replaced by the average on either side of all the points, all the y points on either side for a year. At this point will be replaced by the average on either side for the year, and then give this smoothing point, but it's still going up and down a little bit. It's not a perfect smooth curve, or not a perfectly straight line. So we're getting a moving average. So this is being replaced by an average that moves along through here, and an average that takes the points within a year from but half a year either side of any particular point here. Get that trend. Okay. So take that out now, and what we do now is, having removed this trend from the data, we start to look at averages now. Now we definitely do averages over all Januaries, averages over all Februaries, etc. We can average across all years. We can imagine a more sophisticated approach too that would do a smooth over that, a moving average over that as well. But let's just say for average, we're going to average over all of the years and get this simple summary here. And the last thing it does is make sure that these things all have 0. So it's going to subtract off the average of these pieces so that these all have average 0, and we've got a nice cyclical effect about 0. That means whatever's left over, this minus that will be the residuals. So what have we done? We've done a visual decomposition of the model, and the decomposition corresponds to mathematical decomposition. We've taken the data itself, a time series, we've broken into a piece that is the trend, and a piece that is the seasonality, and then the leftover piece, the residual piece, that is hopefully just some random noise. And so the time series is decomposed into the sum of a few smooth pieces that are interpretable. This is what's happening over time, that carbon dioxide going into the atmosphere is increasing over these decades. This is saying how does it change within any particular year, both interpretable pieces. And hopefully, if we've got these two pieces correct, there should be no pattern remaining in this piece. Okay. So what I suggested briefly in the previous slide is the smooths that I've got here are simple averages. We know that when we did density estimates, we kind of started with averages there, and we ended up with something a little clever, a little thing that had weighted average. So the question is, can we do better than these simple averages? Right. The other thing is that this visual decomposition, that actually seems like a pretty good idea. It's kind of natural with a natural phenomenon like carbon dioxide or sunspots, where we see things changing over time to have a trend and a seasonality component. But can it be used for more than time series? Surely we're not stuck to this just regular pattern of it has to be a regular time series with times that are equispaced, etc. And if we can use it for more than time series, the question is how. So these two ideas I'm going to explore in a moment, just thinking about any data set that are not time series. For example, something like this. Any any two-dimensional data set, can I relate y to x, and can I separate out the pieces of this relationship into interpretable smaller pieces? So that's what we're going to look at momentarily. Okay, let's get started. So just review where we ended last day. And last time we were looking at, we looked at time series to begin with, and possibility of decomposing time series. And then I said, well, time series are typically regularly spaced along the time axis, and you could have anything on that axis, that horizontal axis. So an arbitrary pair of coordinates here, and think about relating y as a function of x. And that gets you back to your regression style of modeling. So you've got y as a function of some mean or central value, which is a function of x, and then some residual variation that's not explained by the model. Okay, that's the irregular part of the model. And last time we talked about, remind you from your first course of statistics, you might use a straight line. And if we fit a straight line to that, it looks like that. And it maybe does not capture that relationship that well. It's certainly increasing from left to right, but there seems to be a lot more going on than just this straight line. So we might want something that adapts a little better to the data that we see. And one way to adapt things that you know about is to just make a much more complicated function mu of x, maybe a polynomial. So some polynomial of some degree p that's going to allow a lot more wiggles in the function and maybe be able to adapt a lot better to the data as we see it. That's sort of a global model for what's going on over all of the range of the x's and beyond. We might want to instead adapt things a little more locally. So last time we talked about just fitting a model at any particular x. So if we're interested in fitting a model at the point x here, we might choose to use least squares as before. Some function here, mu of x, whatever the favorite function is, presumably something simple like a straight line, and have these weights perhaps be highest for those values of xi that are near x, and lower for values that are farther away. So we can use weight at least squares to do that estimation for us at any particular x. So their x's are appearing in two roles here. One, the data points that we have, the xi's, and the other is the location at which we want to find the value of mu, or estimate the value of mu. Okay? So, gave you some weight functions last time. In these functions, you'll see x loc. That's the location that you want to estimate at. The x are going to be the data values that we have. And so we can give unit weights to to points in some range, or we can change the weight. So here's a weight function. All I have to do is calculate the weights for that location, 0.5. Proportion range here is 1, so that's going to be the whole thing. And use the linear model just to fit that straight line. We're only fitting it for that point x equal 0.5, okay, but with those weights. And of course, they're all unit weights, so we get exactly as we had before. This is the same line as I had before, but all I'm interested in is this red dot. That's the fitted value that I'm using these weights for. For some other x, I may use some other weights, okay? So if I change it and make it, I want the weights just to be highest for points that are near the point I'm interested in, and lower points outside. I could have, for example, unit weights for those within some range of the x value of interest, and 0 outside. And you see that changes the line and also the fit where that red dot appears. And I can make that smaller. It's going to be adapting more to the local structure. So here, this is really fitting on all of the gray points here, for which is a red vertical line, okay? And that's the line there. So it's ignoring all these points on either side. Everybody with me? We went over this last day, so this is familiar, a week ago, in much Turkey. Okay, so I could use a different weight function. That was sort of like a boxcar function that everybody got high weight if you're within the range and you got 0 weight outside the range. Maybe I could have one like we had with kernel density estimation, have something that has high values at the x of interest here, x location, so the mean value of a normal density, right? We're setting the mean value there, and then some standard deviation, or if you like, some measure of the span or bandwidth of this weight function. So again, the same point I'm looking at here, but now the weights are diminishing as we more smoothly the farther away we are. Every gray point here is contributing to that red point. Okay, but to varying amounts. The closer the gray point is in the x space to the x of interest, the higher the weight. The farther it is in the x space away from that x value, the lower the weight. Okay, and it's symmetric around the point of interest. So it's a lot like kernel density estimation. And of course, if I change the standard deviation, I make that standard deviation smaller. I'm pulling that Gaussian density in, concentrating on it. So eventually, these points that are very far away are getting nearly 0 weight, asymptotically 0 weight, and move that smaller. And again, it's adapting to the local behavior, but giving more weight within that range to the points that are nearest, and having the weights drop off smoothly as you're moving away from the point that you're interested in. Right? So if we put that together, and I imagine I'm going to do that at a series of 9 different points here. So I'll pick 9 points equispaced across the x space and do a fit here, the red line. You can just see the red dot underneath there, and move that along. So you can see the center of the Gaussian is where the x point is that I'm interested here. I'm in the middle, and just do that fit, so I end up with 9 different fitted lines, 9 different points here, and now I just connect the dots, and that's kind of an estimate of that function mu of x, right? So it's kind of nice and smooth, and it's adapting this locally. I didn't have to decide on what polynomial this would be to try and capture that curvature. Instead, I just let it find the curvature itself by the local weighting. Okay? Right, so again, making the span half the size as it was before, so reducing the standard deviation of the Gaussian and moving along 9 points again. As you might imagine, it's following the local behavior a little more closely, okay, because it's using points that are closest to any one of these blue dots. It's using points that are closest to it with the drop off according to the standard deviation of the Gaussian. And making it a quarter of the original size, so half again. I've got much tinier regions that I'm using to fit any particular straight line. And as I move that along, now my 9 points is a little more jagged, right? It's going up and down following the data a little more. Any questions? Does that make sense to everybody? So I'm just looking at 9 points there and having that weight function move along. And I'm fitting a line at each point, but I'm not using that line. I'm just using the value at that x value, the value on the line at that x value. So if I increase the number of points here, I've got 25 points instead of 9. So I have much more going on between within the range of the x's. So moving that Gaussian along left to right here, all the way across to we're in the middle, and then finally exiting out on the right-hand side. Now I've got a curve that it's got 25 points on it, and it's following the data a lot more closely. Okay? So that bandwidth is going to be, the smaller that bandwidth, the closer it seems to be following the data points itself. Okay? Any questions? Okay, let me formalize that. So I don't want to do it just for, I want to do it for any points that I'm interested in, but I want to have a nice regular way of doing this. And so what we've been doing is we've been minimizing a locally weighted sum of squares. Okay, so I'm going to call this LoWeSS, locally weighted sum of squares. And I'm going to write you a function here that takes these arguments, the data, x and y, the coordinates that you have, the locations, those points at the 25 or 30 or 100, how many points you want to estimate the curve at, the span, this is our standard deviation or whatever, the bandwidth of the thing, a weight function, that Gaussian weight function or that boxcar weight function, your choice, and then the yeah, this is just another thing, equispace locations. If you don't tell me the location, I'm going to choose equispace locations. So here's what the code looks like. So my function is get the range, and what I'll call a bandwidth will be, the argument will be a span. The span is what proportion roughly of the data do you want the weight function to cover. And so I'm going to take that to be the range of the data, the extended range of the data, multiplied by the span, divided by 4 will be my argument I'm going to call bandwidth internally. This is if you don't give me the locations, I'll decide what they are. A vector to collect up my estimates. Remember, I'm going to get estimates at the points that correspond to the x locations. And then I'm just going to go through all the x locations. I'm going to get the weight function, use the weight function to get weights at that x location. I'm going to fit the values now using the straight line model, that LM, linear model with weights given by that weight function. Then I'm going to get the predictions at the x locations that we have. And I'm going to take those predictions and place the prediction inside the value of the estimates. So my mu hat is going to be this vector of estimates. Okay? Does that make sense? Pretty straightforward. And then I'm going to return the x locations and the estimates. So here we go. So if I apply this smooth LoWeSS here, just with the defaults that we have, it's going to produce this smooth curve. And that's kind of nice and following the data fairly closely. Okay? So that function just produces that. So I go get the smooth. It's a smooth version of the data. So one reason we use these smooth is just to get a sense of what's the relationship look like. So we can think about them actually replacing the data points by smooth versions, just to try and capture that structure. How is it varying? How does y vary as x changes? Okay? So this data is fake data that I generated. So we're in the strange position of actually knowing what mu of x is. So I generated this data using normal residuals, normally distributed residuals, in a particular function for mu of x, which means I can actually go and get the function, and it's hidden away here. I've got a mu function that calculates that, and see how it looks compared to the smooth. So the data were generated according to that red dashed function. Okay? And our estimate is this blue smooth curve. So things you can see about this is that it is kind of following that red function fairly well, except at the ends here. And also wherever there are really abrupt changes. I've got these abrupt changes. That smooth is always going to go underneath it. Abrupt changes here, it's trying to smooth out underneath. So it's not going to be able to capture those abrupt changes. What might I do to try and get a chance of capturing those at least more closely? Anyone? Yeah? Yeah, so make that bandwidth smaller. Make that span smaller, right? It'll give me more opportunity to chase these points inside here if I have a smaller bandwidth. Okay. So what I've constructed here is what I call a naive, locally weighted sum of squares estimator. And there's some difficulties with this, which we've already pointed out about not being able to follow the sharp and abrupt changes very well, and some problem with the ends. We have other choices, so how do we choose the bandwidth? If we choose it smaller, we're going to be able to follow abrupt changes more, but we may be introducing abrupt changes that aren't there, right? Because we're following the random noise in the data, so there's this kind of trade-off. And you think about, well, what weight function? I used the Gaussian weight function there, but there might be something else that would be more interesting. For example, a Gaussian weight function, it's a density, so it's going off, it always has positive mass, probability mass, you know, very far away, off to infinity. It asymptotes to 0 at infinity, right? So it's always, every observation is getting some weight. Maybe you want a different function that at some point the weight is 0, that you're not allowing it to appear in the estimate at all. So a number of things you might think about. In R, there's this built-in function called LoWeSS, without the W now. The one we made was just a simple version. LoWeSS here is the same thing, locally weighted sum of squares. Its default weight function is a more robust thing that actually does get down to the axis, Tukey's tri-cube weight. You use the bi-weight, or bi-square weight in the density estimation, I think. So here's a tri-cube weight. And it's, there are other weight functions available that you could use, and it's not restricted to fitting local lines. You can fit local line, local quadratic, local cubic, etc., any local polynomial. Of course, typically, you're only going to use a degree 1 or 2 polynomial, just keeping it simple. So the function is, instead of LM, you've got a LoWeSS. So it's got the formula just as before, y tilde x and data, no weights. The default weights are going to be the tri-cube weights. So if I plot these, again, I get the predictions. I'm getting the predictions now at all of the x values that are in the data set. So predict from the fit, and then I'm just making sure I'm getting them in the right order so they plot properly. And there's the LoWeSS default smooth for this data. Okay. So you might guess by that, but it's not going anywhere near these abrupt changes that we know generated the data. That this bandwidth, or this the span that it's working with is going to be fairly large. Okay. So we can change the span. The default is 0.75. What we're going to use here is 0.15, and if you have 0.15, you'll see that we are in fact tracking the shape of the data a lot more closely. Doing a better job at these abrupt changes, but perhaps introducing some changes that aren't really there in the underlying function because we're chasing local behavior. Okay, so that's LoWeSS with span 0.15, default was 0.75. Any questions? All we're doing is locally weighted least squares, fitting a straight line at each point in the x data. Okay, and using that line to predict what the y value is, and then connecting the dots effectively. Any questions? Those are called smoothers, and that's LoWeSS is a local smoother. If you're interested in this, there's a fair bit of time spent in Stat 444 on smoothers and getting a deeper understanding of how they work. Okay, so spans. If I get a really tiny span, I'm going to follow the data fairly closely. If I get a large span, I'm going to follow just the coarse behavior of the data, right? The largest span altogether with weights 1 is just going to be fitting a straight line to the whole data set. So I've got these spans to play with. Large span, coarse, small span, fine, right? Fine behavior. So I might use these spans just like we did with a time series and decomposing that time series into seasonal trend and seasonality. I might think about, trend is like this long span behavior. Seasonality is this sort of short span behavior. Maybe I could break any smooth down into a couple of pieces like this. So I might, for example, take Y, and suppose our smooth now is S, right? So I use a large span and fit the data, get a large span, and then I've got some leftovers, the remainder, these residual terms, right? So if I have a large span that's going to cover the coarse behavior of the relationship between Y and X, the mean relationship. If I look at the residuals, if there's anything remaining in the relationship between Y and X that's not explained by the coarse summary, it's going to be in the residuals. So I can make the residuals, treat them as if they were on a vertical axis now, right? And then fit another smooth to those residuals with a smaller span. Okay? So I can fit a large span, get some residuals, and then fit a smaller span to chase finer structure, any finer structure. Okay? So here's how we would do this. So let's begin with the large span. The 0.75 is the default for LoWeSS. So fit large will be that LoWeSS. So I've got that nice summary there, sort of S-shaped. That seems to be capturing a sort of first order structure in that relationship. So what I'm going to do then is have a look at plotting that, but then take the residuals here. So I get the residuals from the large fit, and then I'm going to look at these as if that was a plot by itself, and then think about, can I fit those residuals to X now, right? So I have a data frame now that R is the residual and X is X. But with a span that's much smaller. So 0.2 as opposed to 0.75. Get the predictions, add the curve. So same as before, it's just now with the residuals. So my residuals are the gray dots, and I'm using a smaller span to try and get the smooth, any structure that's remaining. And those are the kind of little bumps that we saw before where there were abrupt changes. Okay, so it's trying to capture the remaining structure with a smaller span. Make sense? Any questions? Okay. So I could look again, do this again, and take my small span fit to get the residuals from there, plot, do an even tinier span, now only 0.15 span, to see if there's anything else left after I take the residuals. And I'm hoping that I don't see much left, right? So those are the residuals. Now these are the residuals. The vertical axis here is determined by the residuals from both the large and small spans. That is, I fit the large span, removed it, got the residuals from that, fit a smaller span, removed that span from the residuals, and these are the final residuals. And now that's the smooth that I get trying to describe any structure. That's not a whole lot of nice structure there, sort of coarse structure. Okay? So that's not, they're effectively not any serious pattern left in those residuals. Everybody understand what I've done? Okay. So I could put these various smooths together and think about decomposing this scatter plot. So what am I going to do? I'm going to plot the smooth for the large span, the smooth for the small span, and then the remaining residuals. Okay? So that scatter plot is now decomposed into three pieces. Here's sort of the large pattern that I see in the scatter plot. Here's the second order pattern here with a smaller residual, smaller span. And these are the remaining residuals. Okay? So it's telling a story. There's a bit of a narrative developing here that sort of the core structure is this big thing here, this kind of sinusoidal structure that we see here. Second order is this, and then there's nothing remaining. It's just kind of noise. All right? Now, I've added one other bit of information here, and that's that red rectangle. Now, what's that red rectangle? So backing up here, I'm going to place a rectangle at the far right, which I know is 1.01 to 1.02. And I'm just going to look at the standard deviation of the residuals at the very end, the standard deviation of these guys here. And then I'm going to plot a rectangle that is of 2 standard deviations high, centered at the average of the curve that I'm looking at. So this here, that's 2 standard deviations of these residuals. And I've just placed this bar at the center. This is the same bar. It looks larger here, right, because this doesn't vary as much. This only goes minus 0.4 to 0.4. This goes minus 0.8 to 0.4. So different scale. And it's even smaller here. So if you think about a quick visual test of whether or not these curves are significantly different from 0, you're always doing a test and a t-test looking at what's that mean value look like compared to some scaled version of the standard deviation of the residuals, right? So this little rectangle here is giving you some suggestion, some comparison when you're looking at this plot. Look at how much this varies compared to the variation that remains in the residuals. Look at how much I've captured here comparing to the remaining in the residuals. Okay? Gives you some sense of whether you should believe it. Clearly, I believe that this is significant more than I believe this is significant. Right? Does that make sense? And you can think of other ways of producing a range here rather than just using plus or minus 1 standard deviation. So, question is, well, we did this in a particular order. I took a large span smooth first, then a small span smooth. Why don't we do it the other way around? Okay, let's try it the other way around. So I'm going to fit the small span first. You're going to fit a span of 0.3 and then 0.75 afterwards on the residuals of that. Okay, and plot the results as before. Well, now you see that this small span first, it's a little bumpier, naturally, because it's chasing more local behavior. So it's sort of capturing a lot of the local behavior, leaving little to be captured for the remaining part. And this change here that we're seeing here, definitely by the size of that rectangle, is puny. Right? It doesn't really make sense to do the small one first and then the large one. Because the small one's going to chase the local things, but also the whole large thing, because it's chasing very local behavior. Okay? So that's kind of dumb. Make sense? So how would I build this properly? Because it kind of depends on what the residuals were. And I'd like to have sort of this independence, if I can achieve it at all, between the short span and the long spans. So one way of doing that is to iterate. And so I'm going to do as before, I'm going to take the data, do a long span fit, get some residuals, long span residuals. Take those residuals, do a short span fit, get some residuals. Okay? So we did one step of this. Now, so if I think that I've got a sense of what that short span is, right, I can take it out, that short span behavior, out of the original data and fit a long span to that and get the residuals. If I think I've got a sense of what the long span is now, I'll take that out here, this new long span, out of the original data, and fit a short span. So I'm going to fit a long span, then a short span, then I'm going to take that short span out, fit a long span, get a new long span, take the long span out, get a short span, take that short span out, get a new long span. I'm going to iterate back and forth on this pair of equations. Okay? Until these things settle down. Okay? So just going to move back and forth until eventually I'm hoping that what I'm left with is a long span that's sort of uncontaminated by whatever short span I had, and a short span uncontaminated by whatever I started as a long span, that I'm actually getting close to some independent representation. All right? So I could do that back and forth. Any questions? You could actually do least squares this way if you made all these linear models, just a straight line and complete weights. It's a form of iteration called Gauss-Seidel iteration. How many people have taken Stat 444? Anybody? Okay. You may have seen this stuff with generalized additive models, for example. Similar thing going on. Okay, let's look back at time series. And I want to think about, I'm going to remind you what I did last time when we looked at time series. Time series gave this nice decomposition, which people like to talk about, a trend and a seasonality. We've done similar sort of thing with a long span and a short span. So how did we start with the time series? Okay, with time series with regular spaced times, might look like this. We're looking at the carbon dioxide time series. So you've got the years, and then you've got the season, the frequency here of 12 things that define each year. Okay? So that's kind of the seasonality here in the annual data. And the first thing I did for you to decompose this was a very naive thing. I said, you know what? If I want to see what the seasonality is, I'm going to take the average of all the Januaries, the average of all the Februaries, the average of all the Marches, etc. So I'm going to get that and call that my seasonality, just the average of those guys over all of the years. If I want to get a sense of the trend, I'm going to take the average of each year, right? And look at how does that average year CO2 level change. So that gives me my trend. And that's what I did the first thing. So I looked at the trend there and then looked at the average here for seasonality. And there are several problems with that, right? One is that the seasonality that I'm looking at, we knew it's kind of contaminated by the trend because we know that's going up annually. So it gets sort of the shape of the seasonality, right? But its level is far off. Okay. And I end up with identical seasonality for all years. So that's the first thing I did for you. Another way to behave is to think about any particular month here to try and get the trend, rather than take the average for that whole year. Let's just replace so when I took that average for the whole year, I replaced January by the average of those 12 values, February by the average of those 12 values, etc. Rather than do that, maybe for July, I'll take July to be an average of the guys on either side of it. So that's if I go 6 on either side, I've got what, 13, right? So that's one more month than I want. But if I go 5 on either side, so I've got 5 on either side plus July 11, take the average of those, or give those the same weight, and then go one more month on either side, give them half the weight, and take that average, or that weighted average, and use that for July. The beauty of that is I can do that for every month. Just moving along. It doesn't really need to know the boundary. All it needs to know is what's this frequency that we have, that we got 12, that I want to get a year's worth of observations. So that's going to be a moving average. That's a moving average through that time. For every time period, I'm going to get an average of points on either side. Equally weighted, except at the ends, because I've got an extra one, I'll have half the weight between them. So that seems a little smarter. And that's what decompose does. So decompose does this thing, exactly as I just said. It's going to take a moving average to get the trend, right? And use equal weights except at the outermost points where it's going to be half that size. Okay. Right, and then you can take the trend away from everything, and then do the averaging in the columns. Just average this and get the seasonal components. Given I've got LoWeSS, I could do something a little smarter. So what I'm going to do is that this moving average is effectively a smooth, but using that kind of boxcar, or sort of a boxcar with shoulders, weighting function. I could use any other weighting function I want, so I could use LoWeSS by averaging over years for each month, and then using that average for that month for every year. So smoothing the values for that month over all years. So I'm going to take all of the which way am I going? Over all years. So take a month, go over all of these things and smooth that month over all the years, right? Get that. That'll be for each one of those. And use the smooth value as the estimate for that month for each year. Okay. Similar, instead of a simple moving average, the years, or for the trend component, I could smooth the years themselves after I've removed the seasonality component. So this is what happens here with STL, decomposing time series. This is going to give us the time series as we had before, this carbon dioxide data set, the seasonal component, the trend, and the residuals. And you see that I've got these error bars here that are, in this case, they're roughly the range of the residuals. Not quite, it's a slightly more complex calculation than that, but they're roughly the range of the residuals. So you can see how important that trend is compared to the residual variation, and also the seasonality. And the seasonality is made to be identical, right, for every year. So you're seeing this, every point, every top of this curve is at the same value, every bottom. So it's identical curve being repeated by the way it's constructed. Okay. So I've said most of this stuff, so I can also specify whether I want to fit averages over this window with just by saying the degree is 0, or a local line with degree 1. So here I'm looking at the window of 7. That's on either side, making this a little larger with degree 1. And now I've changed it slightly. And you can see I've got this data as before. And the seasonality is now no longer identical. And this trend is happening here. So I'm allowing the seasonality to change just a little bit and having the trend still cover things. So I'm not forcing it to be an identical seasonality. So I'm getting closer to, if you think about it, our raw data, our short span smooth, and our long span smooth. Okay. So season components now vary a little more over the years, and there are similar arguments for the trend window. So I could choose the smoothing on the trend side versus on the seasonality side, and the size of the window in either one, that's the span effectively, and do different smoothing. So there are a lot of choices here. And in any case, we're always looking for no pattern in the residuals and capturing the major part, the trend, and then seeing what's going on within the frequency term, or within these window of smoothing for that seasonality component. Okay? Right. So, should I do that? I don't think I'll do that. I'll leave that for you to do. If you look at, if you load up Loon and do the demo of the L time series, you'll see that you'll get this nice STL breakdown like that. And of course, you'll be able to pan, zoom, and brush. Like that, so you get a far more interactive exploration of the time series data itself. Okay. So in case you're wondering, this is CO2, a greenhouse gas, contributes to increasing temperature. How much is debatable, but increases the measurements, the time series. You can find that data is still being measured over Hawaii, and so those are the new measurements. That's all we've used in class, and have extended as the same thing is happening, continuing. That trend is going up and up and up and up and up. Okay, so you might have a look at that. So, back to the sunspots. So the sunspots were weird, right? In that it's kind of, number of sunspots per month. So it's kind of annual data. So it's got that frequency of 12. But we know that the cycle is closer to 11-ish years. Right? We investigated that by other means and found it with lag plots, etc. So if I apply STL to the sunspots here, where again I'm going out a little farther to break that clear dependence on the annual. My first cut here's the data, the sunspot data. Here's the seasonal term, which looks like somebody's voice pattern on an audio spectrum. And here's the trend, which is not really very intuitive, right? And that's because it's, in determining the seasonality, it's using that very short span, close to annual span there, which is just not where that seasonality is in the sunspot data. So this is not going to do a very good job. So you can't just throw STL in there and expect it to do a good job, even when you're controlling the span of the smoothing, so you can maybe get outside of the annual thing or inside, however you like. For things that are not going to have patterns that are related to the frequency in which they've been recorded. Okay? So what do I have to do? Well, I'm going to have to get new sunspot data, and I'm going to make a time series from the old sunspots, but instead of frequency of 12 months, I'm going to make it 11 years, or 132 observations. Okay? 11 times 12. And now just plot STL with the same sort of smoothing parameters, so window just of 7 and a straight line. So now there's the data. There's the seasonal component. And there's the trend, if any. It's moving around. That trend is not very significant. If you look at the size of that range box here, it's not very large. The changes here are not large compared to the height of that box. But it is capturing that what we would identify as seasonality in the series. Still a little bit of structure here, so that seasonality is probably not perfectly captured. Again, I'm stuck on months, and the seasonality is probably not 11 years right on. It's probably changing a little bit over time too. Again, there's no reason for the sun to pay any attention to how quickly we orbit it in determining how many sunspots there are, right? So units of the number of orbits we do around the sun is not really that natural for the data itself. But that's close. But that's clearly a better job than that. So we needed those other tools to get a sense of what is that seasonality. If we got to have a sense of seasonality, we can make the time series more amenable to this kind of seasonal trend LoWeSS, right? This STL. Any questions? Oh, I'm done early. No questions? Next Friday, by the way, we have an assignment due, I believe. I will not be giving a class next Friday, so I will ask my TA to appear here to collect assignments, principally because it's convocation.
I promised some people I'd go to convocation. So no class next Friday. I'll send out an email. Any question on the assignment? Anybody started the assignment? Okay, you now can officially do all of the assignment. The last question was with STL, I think.